Yes, dear students, this session is belongs to the paper 5. Previously, we completed 3 blocks. Block 1, reaction mechanism. Block 2, recyclic reaction in offline classes. In online mode, we have completed block 3, that is photochemistry, organic photochemistry. Now coming to the block 4, that is stereochemistry 2. It is the extension to the stereochemistry which we are dealing in the first year. Now, in this stereochemistry topic, we are going to deal with the conformational studies, conformational analysis. Conformational analysis or conformational studies. Okay, in this block, we are going to discuss about the conformations. The first unit in this, the conformations of some aliphatic molecules, and the second unit is, the first unit is in this block conformational analysis or conformational studies or conformations of some aliphatic molecules, and the second one conformations of or conformational analysis of conformations of cyclopentane, cyclohexane, and monosubstituted cyclohexane. Derivatives, and that is the conformational studies, which is in this unit involving the conformations of cyclobutanes, conformations of cyclopentane, conformations of cyclohexanes, and conformations of monosubstituted cyclohexane derivatives. And the third unit is conformational disubstituted conformational studies, conformations of disubstituted cyclohexene and disubstituted cyclohexane and cyclohexanones. In this unit, we are discussed about the conformations of disubstituted cyclohexene, and cyclohexanones. These 3 compounds related conformation studies we are going to deal in the third unit. Next, fourth one. Conformations of few other monocyclic and bicyclic systems. Conformations of some other monocyclic and bicyclic systems. And comparing the reactivity and the conformational stability. That is the 5th unit is dealing with the conformations and reactivity. Conformations and reactivity. This block deals with this 5 units. The first one is conformations of some aliphatic molecules. That is aliphatic acyclic molecules, not the cyclic molecules. Aliphatic acyclic molecules. And second unit is conformations of cyclobutane, cyclopentane, cyclohexane, and monosubstituted cyclohexane derivatives. Anyone joined in the class? Yeah. Am I audible? Archana, Raju? Archana
Yes,
and
sir.
Raju. Am I
Yes, sir.
audible?
Yes, sir. Yes, sir. Clear, sir.
Okay, can I continue?
Yes, sir. Yes, sir. You can.
Right. Now, this third unit, the conformations of disubstituted cyclohexene, and cyclohexanone. These three compounds, conformational structures, stabilities, and their reactivities and their related stability energies, we are going to deal in this unit. Next, fourth unit is conformations of some other monocyclic and bicyclic systems. These are some exceptional from the previous one. Those new compounds, the monocyclic compounds and bicyclic compounds, that may be higher number carbons containing compounds, which we are going to deal here. Next, the fifth unit is dealing with the conformations and their reactivity. Some conformations are reacting more, having a more reactivity, and some conformations are some showing the less reactivity. The relation between the conformation and reactivity, which we are going to deal here. Then coming to the first unit. Yeah, my screen is visible to you all.
Yes, sir.
Yeah. Now the first unit, conformations of some acyclic molecules. First, before going to the topic, we need to understand some definitions. Definitions of some terms. The first one is, what is conformation? What is conformation? Right. Here, this unit is particularly deals with the acyclic compounds. Now, this conformation word not only constrained to acyclic compounds. It is also belongs to the cyclic molecule. Then what is the conformation? Just the isomers which are generated due to the rotation of one or more single bonds present in the molecule. Is there any stereochemical molecule is there? That stereochemical molecule which will generate its corresponding isomer by the rotation of one or more single bond, or rotation of the more than one bonds. Suppose the molecule is having only one single bond, it is undergoing the rotation one single bond. Suppose more than one bond is there, more than one sigma bond is there. All the sigma bonds are associated with CC bond rotation. Therefore, these CC bond rotations results in new isomers, new stereoisomers. These stereoisomers are known as conformers. These stereoisomers are called as conformers, or conformational stereoisomers, or rotamers. The basic thing is, what is definition is rotation of yes, rotation of CC bond around the one or more single bonds, leads to the leads to the formation of new stereoisomers. Leads to the formation of new stereoisomers. Such isomers are known as conformers, or rotamers. Rotamers means the isomers which are generated due to the CC bond rotation, or the conformers which are generated due to the CC bond rotation that leads to the new stereoisomers. Those isomers are known as conformers. These stereoisomers or conformers are conformational stereoisomers are. These are also known as conformational stereoisomers. Conformational stereoisomers. These conformational stereoisomers are dynamic stereoisomers. They are also known as dynamic stereoisomers. Dynamic stereoisomers. Why they are dynamic stereoisomers? I will explain. Dynamic stereoisomers. Right. How these dynamic stereoisomers can be defined, or how we can understand the dynamic stereoisomers? These dynamic stereoisomers are more readily interconvertible, or they are undergoing the interconversion very rapidly. Such stereoisomers are known as dynamic stereoisomers. Here the stereoisomers, that is the conformational stereoisomers, which are generated due to the CC bond rotation in a molecule, or due to the CC bond rotation of with respect to one or more than one single bond. Therefore, these are more readily interconvertible, and the time taking from one isomers to other isomers conversion is very less time. Sometimes we cannot recognizable at room temperature. Therefore, these isomers are interconvertible very rapidly at room temperature. Such kind of stereoisomers are known as dynamic stereoisomers. Always we can treat it as conformational stereoisomers or dynamic stereoisomers. Conformational isomers are dynamic stereoisomers. And here one word is used, rotamers. Rotamers is why we are saying the rotaisomers or rotamers, the isomers which are generated due to the CC bond rotation. Due to the CC bond rotation. Then due to that reason, that is known as rotaisomers. Okay. Now, it was believed that a CC single bond was entirely free in the molecule. Suppose if you take a aliphatic compounds, you can choose a single bond. That single bond is very much free to rotate. When you take two double bonds, can I on the video? You can understand. I am showing my action by my action. Okay, right. Am I visible to you? Right. Look at here. Suppose the two carbons are attached with a double bond, single bond, and a triple bond. The rotation of this is the single bond. You can take it. You can take it. This is the single bond. Okay, whenever you are rotating, it is freely rotated. It is rotated. You keep one particular substitution at the one end is constant. Then you rotate on second end. Then you can get the infinite number of stereoisomers. Those are rotamers or conformational isomers. Rotamers are conformational isomers. Okay. Now, the conformational isomers are generated the pre-rotation of single bond. The pre-rotation is due to a very much free form of the single bond is existing in the aliphatic system. Therefore, more generally, we can see that the conformational generation occurred in the case of aliphatic or fully saturated molecule. Fully saturated molecule can show the conformational isomerism. When you take the diastereomers, so like a double bonded molecule and triple bonded molecule, the rotation, CC bond rotation will be inhibited or blocked. Therefore, they are not undergoing CC bond rotation. There is no free rotation. Suppose if you want to rotate, you need to break the 5 bond. You need to break the 5 bond, then associate the 5 bond. First, you need to break the 5 bond. After rotation, you need to make the 5 bond. But it is a risky task, and it is associated with more energy. Due to that reason, the double bonded compound or unsaturated compound, especially unsaturated carbon-carbon bonds, are not undergoing any kind of rotation. Due to that reason, the conformational structure generation is very much difficult in the case of saturated molecules. Now, this is the definition of conformational isomers. Right. Next. I have already explained that. These are the dynamic stereoisomers. The dynamic stereoisomers means they are interconvertible rapidly at room temperature. Therefore, for the interconversion, the energy required for the interconversion is very much low. That is, the barrier to the rotation about the single bond is very low. Or there is a small hindrance, or the energy is very low, or the small hindrance. The hindrance means there is a hurdle to rotation. The idling of the rotation is very much low. Due to that reason, they are undergoing free rotation. Then they can be detected and distinguished by the physical method. This interconversion can also be identified by using some distinguished physical methods, and we can use for the separation of these conformational isomers we are using, or this interconversion can be studied by using some ambient temperature methods by using some physical method like spectroscopy methods, H1MR like methods. Okay. A study of the physical and chemical properties of molecule in terms of the various conformations is called as conformational analysis. Now, once you are understanding the conformation, once you are understanding the conformational stereoisomerism, after that, you need to study about their physical properties and their chemical properties. This study is known as conformational analysis. Suppose a particular molecule can generate some number of conformational stereoisomers. These conformational stereoisomers, we are comparing their stabilities, comparing their suppose some physical properties like boiling point, melting point, refractive index, like that, or hydrogen bonding interactions, like that, for potential energy stabilization, or if you come into the chemical reactivity, is that undergoing reduction, oxidation, or addition reaction, like that, substitution reaction, like that. When we are comparing one isomer to the another isomer, this study of these physical properties and chemical properties are known as conformational analysis. Now we can make a sentence here: the study of physical and chemical properties of conformational stereoisomers, conformational stereoisomers are known as conformational analysis. Conformational analysis. For this conformational analysis, first you coming to the understanding the stabilities of the compound. Now, here some word is there: dihedral angle. Before going to studying the detailed study of these physical and chemical properties, we need to understand the formation of the conformation. Okay. Here, some word I am using: dihedral angle. Now, you can consider a molecule given in your book also in your course material. Suppose this is the molecule and considered. That means a 2 carbons containing molecule, ethane-like molecule. Now, a conformer may also be defined as a dynamic stereoisomer, the differing only in dihedral angle. Each conformer we can define based on the dihedral angle. The dihedral angle is angle between the two planes, the plane defined by the each fragment. Suppose here there is a ACC bond, one fragment. Here BCC, this is the second fragment. Now, suppose whenever I am taking this a non-planar structure of the above molecule, suppose this is the molecule, we get here. The plane which is passing through, suppose this is the hydrogen, sorry, this is the A, this is the A attached at this first carbon. Suppose if you take the second carbon, this is the B, right? Here the two planes are there. The angle between the two planes, actually the dihedral angle is the angle between the two planes which are passing the same molecule, which are passing through same plane. We get here. Suppose for understanding, I am taking different color pen. Right. Now the plane, we get here. The plane which is passing through the A and these two carbons. The A, this is the one plane. Suppose this is vertical in manner. This plane is vertical in manner. Now the second plane, take this one. The second plane which is passing through two carbons and substituted B. Now this one. Simply can understand this. This is the right. This is the CC bond. This is the one bond, one plane. This is the alpha plane like that. This is the beta, right? Now the angle between these two planes. This is the theta. Suppose if you consider this is the theta. Now this theta, this is the one plane. This is the second plane. The angle between these two planes, theta. This theta is known as angle. This theta is known as dihedral angle, right? Now, from this we can easily define that. Already I have given the definition: the angle between the planes which passing through the same molecule is known as dihedral angle, right? Suppose the same dihedral angle we can observe in the Newman projection formula. You can take the same molecule in the Newman projection formula. You know that the Newman projection formula is like this. The circle represents the rear carbon. The center of the circle which represents the front carbon, right? The C1 is this one, the dot, right? Now, are the three substitutions on carbon 1. This is the A. Remaining, you can take any other substitutions. This is the A, right? Now, the second substitution at the rear carbon, second carbon. Now, this is the B, and the remaining are this. Now, suppose we get here. I am showing the planes here. How planes are arranged. This is the one plane which is passing through the carbon A. Now, okay, this is the one plane. right? The second plane, that plane is passing through, look at here. This is the second plane. Now this plane, this is the plane. These planes are separated by some degrees of angle. Now this is the angle theta, is known as dihedral angle. That means we can show the dihedral angle by using Newman projection formula. Now this dihedral angle is also known as torsional angle. This torsional angle is having the directional properties. Okay, this dihedral angle is also known as torsional angle. Torsional angle, but it is having directional properties. Is having directional properties. Right. Now, suppose torsional angle is the smallest value of dihedral angle. That is, here the some representation is given. Look at here. Some example is taken for the understanding the torsional angle and dihedral angle. When we are called the torsional angle, when we are called the dihedral angle, because by using the directional property, where the minimum angle is there, that is the suppose if you are rotating clockwise or anti-clockwise, that is the plus direction and minus direction. If you are rotating minus degrees, minus 30, that is equal to the plus 240. Okay. Suppose if you are rotating 180 degree, that may be plus 180 minus 180. Wherever the minimum amount of angle of degree is there, whether it is a plus direction or minus direction, that is considered as torsional angle. That is considered as torsional angle. For example, the same molecule is representing various forms of or various conformations of conformation structure in the form of Newman projection formula. Suppose this is the molecule which we are taken in general, taken for the example. Now it is presented in Newman projection formula, a circle, there is a rare carbon and its cycle, right? It is the first we are taking it as eclipse structure. The A front carbon, the back carbon is having remaining are same. Now this is the first structure. This is known as schizoid. This is known as schizoid eclipsed structure. Eclipsed conform. Right. The same. If you are rotating 60, this is the carbon, first front carbon, this circle is the rear carbon. Now we are rotating, that is the CC bond is there. Just we are rotating 60 degrees. Now here I am to rotate 60 degrees. Rotate the CC bond. 60 degrees CC bond rotation. 60 degrees CC bond rotation. Then it leads to the some Gaussian structure. Again, I'm drawing a circle. This is the rear carbon. Center of circle, that is front carbon. Now I'm keeping the constant A. Just the rear carbon is I'm rotating. The rear carbon I'm going to rotate here. Now it's a new conformer. I'm some particular angle of rotation. Suppose it can generate in between the 0 to 60 degrees angle, infinite number of conformations by using the fraction of angle. But for understanding the standard observation, I'm maintaining the standard degree of rotation. Right now, this A is the standard position. Now B is rotated 60 degrees rotated. Now B is here. Now this direction is clockwise direction, therefore known as plus. Plus. The plus may be represented in the form of P. Now this is named as, actually this is the Gaussian conformation. The direction is clockwise, therefore P Gaussian conformation. P Gaussian conformation or conformer. Right? Now here in the first case, the dihedral angle is, I'm just using dihedral angle. DHA dihedral angle. It is 0 degrees. And torsional angle is also, torsional angle is equal to TA. Torsional angle is also 0 degrees. In the case of first. When you come to the second conformer, that is the para-Gaussian conformation, the dihedral angle is 60. Dihedral angle is 60 degrees. You're not minus. This is just I'm using for. Now, when we coming to torsional angle, you need to represent the rotational angle, either it is the clockwise or anti-clockwise. Now, whenever you are showing the torsional angle, it is the plus 60. In the case of simple angle, you don't need to mention the directional codes or directional symbols, but you need to represent directional symbol that is the plus 60 degrees. Right? Again, the total rotation is 120 degrees. Again, I'm going to rotate 60 degrees rotation. CC bond. The total is from G1 next to total is 120. But from the second onward, I'm making to 60 degrees rotation. CC bond. The result. Just I'm removing the B from here. Here A position, no change in position. B is here. Now this is the confirmation. Third confirmation. Okay. Now the degree, total degrees, this is known as 120 degrees eclipsed structure. This is also known as eclipsed, partial eclipsed, or 120 degrees eclipsed structure. Eclipsed conformer, or can also named as partial eclipsed. Partial. Now, when you come into the dihedral DHA, it is 120 degrees. DHA is 120 degrees, right? But torsional angle, both are same angle, but it is the directional property, that is plus 120. Plus 120 degrees. Right. Now, the next 120, now next degrees, the total is 180 degrees. The total 180 degrees rotation, 0. First one to next one. This is 60 degrees CC bond rotation. Then it leads to Gaussian or staggered conformation. You can call it a staggered or conformation. No, you can use it. It's the fourth structure. Previous one is, it is the fourth one. This is known as anti-conformer. Known as anti-conformer. Now the dihedral angle is 180 degrees. No directional property, but the torsional angle is plus or minus. You can use plus or minus 180. Or here also you can mention torsional angle is 180 degrees. No need to represent here directional property, because when you moving clockwise or anti-clockwise in 180 degrees, it results the same conformational structure. Due to that reason, whenever you are mentioning the torsional angle, when it is the 180 degrees, without directional property also we can mention it. That is the same as dihedral angle. Right. Next 60 degrees rotation. Yeah. From this is the 60, this is 120 degrees. After results, it is 180 degrees. Right. Next, after 60 degrees, 60 plus 180, that is 240. Again, the 60 degrees bond rotation. CC bond rotation. Now, again, it results eclipse structure. That is the 240 degrees eclipse structure. It's the front carbon. Right. This is the A. The B is here. Now, this is known as 250, 240, 240 degrees eclipsed conformer. Eclipsed conformer. Now, the dihedral angle is 240 degrees. And the torsional angle is, now you need to reverse anti-clockwise. That is the minimum angle. Here the torsional angle, dihedral angle is differentiated by the dihedral angle. We are taking only one direction, but the torsional angle we are choosing the direction where it gives the minimum angle. That is here 120 minus 120. Right. Now again 60 degrees rotation. CC bond rotation. Now it leads to the play position will be changed. This is the fifth one actually. Now the sixth one. This is known as Metagashi conformer. Why Metagashi? The rotation, whenever we are considering the torsional angle, it rotates the minus 60 degrees. Minus 60 degrees. That minus 60 degrees rotating the Gaussian conformer. Now this is known as Metagashi or Gaussian conformer. Metagashi conformer. Now dihedral angle is DHA is 300 degrees rotation. Next, the torsional angle is minus 60 degrees. Now, just by simply we can understand that what is the difference between the torsional angle and what is the torsional angle, what is the angle. Again, you rotate the 60 degrees rotation CC bond. It gives the initial one, original one. Now, this 1, 2, 3, 4, 5, and 6 are known as conformational isomers. Structure 1, 2, 3, 4, 5, and 6 are known as conformational isomers. Conformational isomers. And also there are also dynamic stereoids. Dynamic stereoids. Right. Okay. Now coming to some terminologies are there. That is Klein-Trilog terminology for giving the designations of conformance based on the torsional angle. For giving the terminology or for giving the designation to the conformations based on their torsional angle. Now take the heading Kiliani. We can take the Kiliani. K-L-Y-N-E. Trilog terminology. To assign or to give designations of conformations based on torsional angle. Now, for specifying torsional angle, two hydroxyl groups, one on each carbon atoms are required. Here the hydroxyl atoms means hydroxyl atoms or groups means there is the referred group. They are the considered group. Those groups arrangement based on those groups or atoms, we can give the torsional angle for that molecule. If all the substituents on the carbon atoms are different, the sequence rules preferred group that is we know the CIP rules. That CIP based on the CIP rules, we can give the sequential rule. We can apply the sequential rule. That sequential rule give the some preferred group. That preferred group is selected. For example, here the stilbene is there. It is pH dichlorostilbene. Now, in this case, we need to apply the CIP rules. Based on the CIP rules, we need to select the groups. Here, based on the CIP rule, the chlorine gets the first priority, the carbons, and like phenyl group gets the second priority, hydrogen gets the third priority. Similarly, it is the third priority. Now, these chloride atoms are considered to identify the torsional. Next, second rule. If two substituents in a set are identical, that is, the two substituents are there on the two carbons, or they are like a set-like molecule or identical groups or atoms. The non-identical groups is selected irrespective of the sequence rule. For example, hydrogens are the hydroxyl groups in a molecule 1,1, 2,2 tetrabromoethane. Even though sequential rule gives the highest priority atom, but the highest priority atoms are more atoms are there on the group on the carbon, the less priority group will be considered to identify the torsional angle as a selected group or atom. For example, here a carbon-carbon ethane, that is bromine, and bromine, and it is attached with hydrogen. This is the what is that? It give the 1, 2 numbering. 1,1, 2,2 tetrabromo. Now, As per the CIP rule, the bromine gives the first priority, but all are bromines. We cannot decide which one is the pi-digital atoms. In such case, the least priority group, hydrogens are only having one hydrogen and one carbon, and other hydrogen and second carbon. Therefore, the two hydrogens are there. This pair is considered as pi-digital atoms. Pi-digital atoms to identify the torsional angle. Next, third rule. Third rule is if all the substituents in a set are identical. In such case, one set will be considered. For example, ethane is there. Simple. Each carbon is having 3 hydrogens. Each carbon is having 3 hydrogens. Now, in such case, you need to number them 1, 2, 3, 1, 2. Now, the number, whatever it is considered as one set, considered as pi-digital atoms. Next. Here some terms are given, are used for the designation of conformance. Some terms are used for the designation of of conformance. The first one, you can use a rotational direction, that is the plus or you can use that plus or minus directions, that is the clockwise or anti-clockwise are used for rotation of 0 to 180 degrees 180 degrees in clockwise or anti-clockwise. Clockwise or anti-clockwise. Respective. Clockwise or anti-clockwise directions respective. Right. The second one. This is the designation plus and minus designations we can use. And also use sin for the, can give the designation sin for a value of angle rotation, for a angle of value of 0 to 90 degrees rotation. And we can give the anti for a value of 90 to 180 degrees, 90 to 180 degrees rotation in both the direction. It may be clockwise direction or anti-clockwise direction, in both the direction. In both the directions, right? Next. Sin and anti terminology. The first one is the plus and minus terminology, and the second one is sin and anti. And the third type periplanar, nearly periplanar, cleaner. Periplanar means here you can take periplanar. Here this periplanar will be again divided into planar and cleaner. Here the planar means flat. It means flat. This cleaner This means that incline is known as incline. Now, here these terms can be easily understood when we are making a circle. The circle is having a certain center. Okay. Suppose you take this circle, right? May not be exact circle, but okay, here just treat it as a circle. I am dividing this circle into two halves. I'm dividing the circle into two halves. Look at here. I am making here 0 angle. This is the 0 degrees angle. Now it is treated as 180 degrees. 180 degrees angle. Right. Now it is the clockwise rotation. It is then plus 90 degrees. It is the anti-clockwise direction. It is minus 90 degrees. Right. Now, in between the 0 and 90, there is a two divisions are there. One is the 30 degrees and another one is the 60 degrees. This is known as 30 minus 30 and this is the minus 60. Similarly, it is the plus 30. It is the plus 60. Right. Now, is a two divisions between the 90 to 180. 90 to 180. That is, one is taken as 120. 90 plus 30. 120. That is plus 120. And another angle 120 plus 30, 150 plus 150. Similarly, in this case also, this is minus 120. This is minus 150. Now you join it. That 30 degrees is equal to the 150. That is matched with the cross section. Next, minus 150 is matched to plus 130. That is exactly anti to each other. You can say that. Now, here we can get the 4 parts in the circle. So 6 parts in the circle. This is 1, 2, 3, 4, 5. The 6 parts. The first part we can show that we indicated that R minus SP. The SP means plus R minus. We are using the word sin periplanar. Sin periplanar. And the second one, it is indicated with plus SC. Plus SC. SC means plus sin synclinal. That is linear. Right. The third one, plus AC. Plus symbol, sorry. Yeah. Plus anticlinal. Plus anticlinal. And fourth one, plus or minus AP. That means plus or minus anti-periplanar. Anti-periplanar. Next, fifth one, minus AC. That is minus anticlinal. And the sixth one, yes, SC. Sorry, SC. Minus synclinal. These are the 6 parts. Based on the 6 parts, we can give the conformational structural names. Okay, then here all these things I'm making into a small table. If we consider the first one is the torsional angle. Torsional angle. And further to after assigning the torsional angle, we need to assign the designation. And a symbol. References. We are using some compound reference. It is a now dihedral angle is multiplied with 60. How many times it will be multiplied? Suppose it is taken as n into, then it is n we are represented here. Now the first one 0 to 0 degrees to plus or minus 30. Plus or minus 30. This is known as plus or minus syn periplanar. Syn periplanar. The designation is plus or minus 60. Next, the structure is known as cissoid. Cissoid eclipsed. Eclipsed. This is the first structure when we are here given the conformation structures. Okay. Here I have given. This is the cissoid. This is the syn periplanar structure actually. Syn periplanar plus or minus syn periplanar. Right. Now that is structure 1. That is mentioned in the brackets. The common number 1. I'm giving a big. Now the dihedral angle is multiple of n. It is 0. 0 into 60. Now 0. That is the dihedral angle. The dihedral angle is 0. Dihedral angle into 60 is equal to the angle is multiplied with 0. Therefore, the dihedral angle becomes also 0. Right? Now, plus 60 to what degrees? 20. Plus or minus 30. Plus 60 plus or minus 30. That is plus or minus 30 degrees. Now this is known as synclinal plus synclinal. The plus 30, 90, minus 30, plus 30. Then synclinal, it is indicated with plus SC. Now this structure is known as Gaussian. Whatever the structure is observed in the second structure in the previous conformation. Para-Gaussian. In the structure 2. Now the dihedral angle is multiplied with 1 into 60, that is the 60 degrees. That is known as dihedral angle. That means you can see that the dihedral angle between the 60 degrees, that is 0 to 90 degrees, the angle is known as 60 degrees. That multiple in between these two angles, the angle is 60 degrees is considered as dihedral angle, right? Now, coming to the plus 120 degrees, plus or minus 30. If it is the minus 30, 120 minus 30, that is 90 degrees. If it is the plus 30, 120 plus 30 is equal to 150 degrees. Now this is considered as plus anticlinal. Plus anticlinal, that is plus AC, it is mentioned with plus AC. Now this is 120 cissoid structure, eclipsed structure. Eclipsed conformer. Eclipsed conformer. Now the dihedral angle is multiple of 2. 2 into 60, 120. Is okay. Now, this is the actually third structure in the above given conformational structures of ACB. Next, we coming to the 180 degrees, the plus or minus 180, or you can take it as a without directional property 180 plus or minus 30 degrees. Now this is known as plus or minus anti-periplanar anti-periplanar. Now this is plus or minus AP shown with the. Now this structure is called as anti-structure. Structure is known as anti-conformer. Now the fourth structure is mentioned in the previous given conformation conformers. Now it is the multiple of 3 into 60 degrees. That is 3 into 60 is 180. Okay. Simply you can make it. The first angle is divided with the 60. Is divided with the 60. It is divided with the 60. Is divided with the 60. Now divided with 60 is multiple of 3. It is the multiple of 2. Is the multiple of 1. Is the multiple of 0. Like that. That is taken. Next. Again the minus 120. It is the angle is minimum is considered minus 1 plus or minus 30. That is known as anticlinal. That is minus anticlinal. Minus anticlinal. Now minus AC. It is known as 240 as per the dihedral angle. 240 eclipsed conformer. That is one. It is the multiple of 4. Actually, this is the dihedral angle is considered multiple of 4 into 60, 240 as per the dihedral angle. As per the dihedral angle, multiple of 4. As per the torsional angle, multiple of 2. Multiple of 2. Torsional angle. Right. Next, minus 60 degrees plus or minus 30. It is the last one. Minus synclinal. Minus synclinal. That is minus SC. It is known as M Gaussian. You need to remember all these structures name: meta Gaussian, para Gaussian, or M Gaussian, P Gaussian, anti-conformation, cis eclipsed, or partial 240 partial eclipsed, and 120 eclipsed. You need to remember these all these terminologies are used in the future studies of the conformational studies of the cyclic compounds and the cyclic compounds. Right now, it is the multiple of 5 because here the 240 plus 300 degrees. This is the 300 dihedral angle rotation. Now the 300 divided by 60. 5. Now this table clearly explains that which one is the cissoid eclipse. That is the syn-periplanar plus or minus syn-periplanar is known as cissoid eclipse, and plus synclinal is known as Taragashi, plus anticlinal is known as plus eclipse conformer, plus or minus anti-periplanar is known as anti-conformer, and minus anticlinal structure is known as 240 eclipse conformer, and minus synclinal structure is known as Metagaussian conformer. Okay, these are very much helpful to understand the conformational structures of the CC bond acyclic compounds, and which they are undergoing rotation to generate the several kinds of conformations. Now, these designations of a conformers are the signs of the torsional angle in it remains unchanged whether the molecule is viewed from the front or rear. You can utilize these torsional angles and observe the molecule. Either it may be front side or back side. Suppose if you are seeing the rear carbon first, or if you are seeing the front carbon first, whatever it may be, the torsional angle conformation designations will not change. These designations will not change. That is the the molecule is viewed from the front or rear side, the designation remains unchanged. And in the first case, the torsional angle is measured from A to B. In the second case, from B to A, where A and B are the fiducial groups here. By taking the fiducial groups reference, we are giving the assignments or designations to the torsional angles. Right? Now, stability of conformance. Just this last topic I will cover, and then I will close the session. Right? Stability of conformance. Coming to the stability of conformance. Now, if a molecule can take conformation with lowest energy, then it is attains the more stability. If you take any conformer, it is always existing in the form of a one particular stereoisomeric conformation structure. That conformation structure at room temperature attains the highest stable. That is known as stable conformation, or that is known as stable conformational isomer. Now, the energy of a conformation is affected or is influenced among the other things by torsional strains, van der Waals repulsions, dipole repulsions, and intramolecular hydrogen bond. You can hear, once you consider the conformation structure, it is a stable conformer. That stability is influenced by several factors like torsional angle, torsional strain, that is also known as steric hindrance, and van der Waals repulsions, dipole repulsions. Next to intramolecular hydrogen bonds. All these factors are influencing the stabilities of the conformation structures, stabilities of conformations. When two bonds are attached to adjacent carbon, which are eclipsed to each other, they will be repulsive interactions between the electron clouds of the bonds. Suppose previously I have mentioned this structure in the Newman projection formula. If you represent this is conformation as eclipse conformation, that means each attached sigma bond on each carbon is overlapped with other. This is the sigma bond of first front carbon is overlapping the sigma bond present on the rear carbon. This is known as eclipsing. Due to this eclipsing, this is known as eclipsing of atoms or groups. These eclipsing of atoms or group, there will be a repulsion between the electron cloud. Here, these are the two bonds electron clouds are there. Due to that, there is some repulsions are there. That is one factor. Now, these repulsions are, there is a repulsion between these, the electron density of one carbon or one bond to the electron cloud of the other bond. There is two bonds are there, the two bonds are one over the other. There is interaction. The interaction may be repulsive or attractive. Here the repulsive interactions are more influential because both are same charge. There are repulsions between them. These repulsions are known as torsional strain. This repulsion is known as torsional strain, are also called Fidger strain. This is same thing is also known as Fidger strain. F-I-D-E-R. Fidger strain. Eclipsed strain. Due to the eclipse, this strain is occurred. Due to that reason, this is also known as eclipsed strain. Right. And this is also last name is bond opposition or bond opposition strain. The same torsional strain, we can name it as strain, or name it as eclipse strain, or we can name that as bond opposition strain. Now, when two non-bonded atoms, they are not connected to each other by bond, are known as non-bonded atoms or groups. That means the groups are or atoms are not directly connected or linked to each other, are close together. Then the sum of their van der Waals region. Look at here. Here you consider a conformer in the new conformer. So rotating 60 degrees, the bulk groups are there. Here groups are there. These bulk groups having some particular van der Waals region. Van der Waals region is the electron cloud which will be extended at the maximum extent. That is known as van der Waals region. Each group or atom is having particular van der Waals region. These van der Waals regions are of the adjacent groups are having particular van der Waals region. These van der Waals regions are come together. There is a repulsion interaction may be generated. These interactions are known as van der Waals repulsions, or these are known as van der Waals interactions. These van der Waals interactions may be a repulsions. These are known as van der Waals repulsive forces, are also known as non-bonded interactions or non-bonding steric interactions. These are known as non-bonded steric interactions. Commonly, we can say that van der Waals repulsive forces are non-bonded repulsion. For example, this we can consider. Or other example, the van der Waals radius of hydrogen atom is 1.2 angstrom. When two non-bonded hydrogens are close together, the van der Waals region combinedly 2.4 there will be a van der Waals repulsions between those two are occurred. These are known as non-bonding interactions. Non-bonding interactions. Okay. Next, dipole-dipole interactions. Here, due to the electronegativity difference between the groups or atoms attached to a bond, there is a unequal distribution of bond pairs takes place. Unequal. Suppose there is A and B is there. There is a electronegativity difference is there. It is the more electronegative, it is the less electronegative. Always this bond pair is more towards A, therefore it is always the partial negative charge. This bond pair is more towards the A, therefore it becomes electron deficient. Then it partially gets the partial positive. Now this generation of charges, partial charges, are known as dipoles. Now, when a molecule is showing conformational isomerism, but they are having dipoles, these dipoles, the same kind of dipoles are come to closer, there is a repulsive interactions are generated. These repulsive interactions are known as dipole-dipole interactions. These interactions are known as dipole-dipole interactions. Okay. Now, next one. Intramolecular hydrogen bonding. The fourth one. The first one is torsional strain. There is a bond overlapping that is due to the torsional strain. Van der Waals repulsion, that is due to the overlapping of van der Waals regions of the two groups or atoms adjacent to each other. Next, the third one is the dipole-dipole interaction. This dipole-dipole interactions is due to the generation of the already existing of the dipoles in the molecule. These these groups are come to closure. They may be a result of repulsions or attractions, where the opposite charges are come together. There will be a attraction, or same charged ends are come together, that results in repulsions. Now the repulsions are known as dipole repulsion. The interactions are attractions are known as dipole-dipole attraction. Okay. Next, similarly, here hydrogen bonding, intramolecular hydrogen bonding, where a highly electronegative atom partially donates its pair of electron to the hydrogen, which is attached with the highly electronegative atom. There is a partial interaction between the hydrogen and electronegative atom. This is known as hydrogen bond. This hydrogen bonding is established within the molecule. It restricts the CC bond rotation. Therefore, Once the CC bond is restricted due to the hydrogen bonding, the stability may be increases. Okay, therefore, these four factors: torsional strain, van der Waals repulsions, dipole-dipole repulsions, and intramolecular hydrogen interactions or attractions always influences this stability of conformational structures. Okay, this is about the stability of conformations. Now, next we are going to discuss conformational structures of ethane and substituted ethanes of acyclic compounds. Okay, thank you very much. If you have any doubts, you can ask me. I will rectify it. As all of you followed?
Yes, sir.
Yeah, Nagesh Kumar, are you following?
Yes, sir.
You are. I just tell you one thing. Conformation structure. When you are seeing just a overlook on the topics, it will appear like a difficult topic. Whenever we are going through with a keen interest, it will be very easiest topic than the other. Understand?
Okay.
Okay.
Okay, thank you, sir.
If you have any doubts, you can ask me. Okay, thank you. I'm closing the session.